Download this code from codegive.com, link in the description below. Certainly. The transformer architecture is a foundational model in the field of natural language processing, NLP, and is the basis for many large language models, LLMs, today. In this tutorial, we will explore the key components of the transformer architecture, specifically focusing on the architecture described in Attention Is All You Need by Vaswani et al., 2017. We'll also provide a simple code example using PyTorch to illustrate how the transformer operates. Overview of the transformer architecture. The transformer architecture consists of an encoder and a decoder. One encoder, the encoder processes the input sequence and generates a set of continuous representations. It is made up of multiple layers, each containing two main sublayers. Multi-head self-attention. Feed-forward neural network, FFN. 2 decoder, the decoder generates the output sequence from the encoder's representations. It also consists of several layers with 3 main sublayers. Masked multi-head self-attention. Multi-head attention, attending to encoder outputs. Feed-forward neural network, FFN. 3 positional encoding. Since transformers do not have a built-in notion of sequence order, positional encodings are added to the input embeddings to maintain the order information. Key components. 1. Multi-head self-attention. This mechanism allows the model to focus on different parts of the input sequence when producing an output. It uses multiple heads to capture different types of relationships. 2. Feed-forward neural network, FFN. After the attention mechanism, the output is passed through a feed-forward neural network, which applies a nonlinear transformation. 3. Layer normalization and residual connections. Each sublayer is followed by layer normalization and a residual connection, which helps in stabilizing the training. 4. Output layer. In the decoder, the final layer typically uses a softmax function to produce probabilities for the next token in the output sequence. Code example. Here's a minimal implementation of the transformer architecture in PyTorch. This example focuses on building the encoder part of the transformer. Python. Import torch. Import torch.nn as nn. Import torch.nn.functional as f. Class positional encoding, nn.module. Def__init__, self, d_model, dropout equals 0.1, max_len equals 5000. Super, positional encoding, self, .__init__. PE equals torch.zeros, max_len, d_model. Position equals torch.arrange, 0, max_len, type equals torch.float, .unsqueeze, 1. div_term equals torch.exp, torch.arrange, 0, d_model, 2, .float, asterisk dash, torch.log, torch.tensor, 10,000.0, /d_model. PE:02 equals torch.syn, position asterisk div_term. PE:12 equals torch.cos, position asterisk div_term. PE equals PE.unsqueeze, 0, .transpose, 0, 1. Self.register_buffer, PE, PE. Self.dropout equals nn.dropout, dropout. Def forward, self, x. X equals x plus self.pex.size, 0, smiley face, return self.dropout, x. Class multi-head attention, nn.module. Def__init__, self, d_model, number_heads. Super, multi-head attention, self, dot underscore underscore init underscore underscore. Self dot number underscore heads equals number underscore heads. Self dot d underscore model equals d underscore model. Self dot head underscore dim equals d underscore model / number underscore heads. Assert. Self dot head underscore dim asterisk number underscore heads equals d underscore model. D underscore model must be divisible by number underscore heads. Self dot values equals nn dot linear, d underscore model, bias equals false. Self dot keys equals nn dot linear, d underscore model, bias equals false. Self dot queries equals nn dot linear, d underscore model, bias equals false. Self dot fc underscore out equals nn dot linear, d underscore model, Def forward, self, x, n, sec underscore length, underscore equals x dot shape. Values equals self dot values, x. Keys equals self dot keys, x. Queries equals self dot queries, x. Values equals values dot view, n, sec underscore length, self dot number underscore heads, self dot head underscore dim, dot permute, 0, 2, 1, 3. Keys equals keys dot view, n, sec underscore length, self dot number underscore heads, self dot head underscore dim, dot permute, 0, 2, 1, 3. Queries equals queries dot view, n, sec underscore length, self dot number underscore heads, self dot head underscore dim, dot permute, 0, 2, 1, 3. Energy equals torch dot einsum, nqhd nkhd nqhk, queries, keys. Attention equals f dot softmax, energy / self dot d underscore model, 1/2, dim equals 3. Out equals torch dot einsum, nqhk nvhd nqhd, attention, values, dot reshape, n, sec underscore length, self dot d underscore model. Return self dot fc underscore out, out. Class feed forward, nn dot module. Def underscore underscore init underscore underscore, self, d underscore model, d underscore ff equals 2048, dropout equals 0.1. Super, feed forward, self, dot underscore underscore init underscore underscore. Self dot fc1 equals nn dot linear, d underscore model, d underscore ff. Self dot fc2 equals nn dot linear, d underscore ff, d underscore model. Self dot dropout equals nn dot dropout, dropout. Def forward, self, x. Return self dot fc2, self dot dropout, f dot relu, self dot fc1, x. Class encoder layer, nn dot module. Def underscore underscore init underscore underscore, self, d underscore model, number underscore heads, d underscore ff, dropout equals 0.1. Super, encoder layer, self, dot underscore underscore init underscore underscore. Self dot self underscore attention equals multi-head attention, d underscore model, number underscore heads. Self.ffn equals feed forward, d underscore model, d underscore ff, dropout. Self.layer underscore norm 1 equals nn.layer norm, d underscore model. Self.layer underscore norm 2 equals nn.layer norm, d underscore model. Self.dropout 1 equals nn.dropout, dropout. Self.dropout 2 equals nn.dropout, dropout. Def forward, self, x. attention underscore out equals self dot self underscore attention, x. X equals self dot layer underscore norm 1, x plus self dot dropout 1, attention underscore out. FFN underscore out equals self dot FFN, x. Return self dot layer underscore norm 2, x plus self dot dropout 2, FFN underscore out. Class encoder, NN dot module. Def underscore underscore init underscore underscore, self, src underscore vocab underscore size, d underscore model, number underscore heads, number underscore layers, d underscore ff, dropout equals 0.1. Super, encoder, self, dot underscore underscore init underscore underscore. Self dot embedding equals nn dot embedding, src underscore vocab underscore size, d underscore model. Self dot positional underscore encoding equals positional encoding, d underscore model, dropout. Self dot layers equals nn dot module list, encoder layer, d underscore model, number underscore heads, d underscore ff, dropout, 4 underscore in range, number underscore layers. Def forward, self, x. N, sec underscore length equals x dot shape. X equals self dot embedding, x. X equals self dot positional underscore encoding, x. For layer in self dot layers. X equals layer, x. Return x. Example usage. src underscore vocab underscore size equals 10,000 example vocabulary size. D underscore model equals 512 model dimensionality. Number underscore heads equals 8 number of attention heads. Number underscore layers equals 6 number of encoder layers. D underscore ff equals 2048 feed forward network dimension. Dropout equals 0.1 dropout rate. Encoder equals encoder, src underscore vocab underscore size, d underscore model, number underscore heads, number underscore layers, d underscore ff, dropout. Sample underscore input equals torch dot randint, 0, src underscore vocab underscore size, 32, 100, batch size of 32, sequence length of 100. Encoder underscore output equals encoder, sample underscore input. Print, encoder output shape, encoder underscore output dot shape, should be, 32, 100, 512. Explanation of the code. 1. Positional encoding. This class creates positional encodings using sine and cosine functions and adds dropout for regularization. 2. Multi-head attention. This class implements the multi-head attention mechanism. 3. Feed-forward. This class implements the feed-forward neural network used in each encoder layer. 4. Encoder layer. This class represents a single layer of the encoder, which includes self-attention and a feed-forward network, along with normalization and dropout. 5. Encoder. This class constructs the entire encoder, consisting of an embedding layer, positional encoding, and multiple encoder layers. 6. Example usage. We create an instance of the encoder class and pass a random input tensor to simulate processing a batch of sequences. Conclusion. The transformer architecture is a powerful and versatile model for processing sequential data. Its ability to capture long-range dependencies through self-attention mechanisms has revolutionized the field of NLP. The code example provided illustrates the basic structure of the encoder part of the transformer. You can extend this code to implement the decoder and train the model on a specific task.